today about IMFs, and you're going to want to write this down because you are going to be held responsible for them. You guys have some paper? This is notes. IMFs are intermolecular forces. Okay, we have been working with bonding. We've been working with ionic, covalent, polar covalent, metallic bonding. This is between elements, so they make compounds. IMFs are between compounds, so two compounds together, and how the forces interact between them. We're going to start with the weakest one. For the most part, there are some exceptions to the rule, and we go over those in AP, but you just need to know that they're the weakest. Okay, and these are called LDFs. And we like to use little acronyms and phrases. LDFs represent London, I should use a capital for L, dispersion forces. Anybody ever been to London? Okay. Every morning there's fog. Every morning there's fog. And so this is sort of where they've got this London dispersion forces. Every morning there's fog. Where it comes from, who knows, whatever, it's always there. Okay? This force between molecules is between every molecule we have. It's sort of like you got assigned to this room, so whether or not you like it as a class, you have LDF. Even if you hate the person across the room. Okay? You have LDF. You have something in common. We don't know exactly what it is other than you're in this classroom. So two molecules will have LDS if they're close to each other. Okay? So if I look at this, basically it could be like a carbon and a hydrogen, and we have our hydrogen that we learned how to draw out like this, or we're going to, and a hydrogen coming out like this, and a hydrogen just in the plane. Anybody remember what shape this is? Tetrahedral. This is a tetrahedral shape, and it has an angle of 109.5, right? Degrees. This was the one that I showed you that I actually made up, and I took and I turned and I turned and I turned, and it looked the same no matter how I dropped it. Okay? Hydrogens will want to give up their electrons. And so they'll have a slight positive charge. This is what's known as a small delta. So most of you know delta as change looks like that. That's a capital delta. This is a lowercase. Okay? So we have positive deltas out here around. Well, in this case, carbon is actually taking on, so it actually has a slight negative charge. Now, in this kind of bond, this is a covalent bond. One's a little bit stronger than the other. It's like a tug of war. Okay? So carbon's tugging at those electrons a little bit more than hydrogen is. So those electrons are closer to hydrogen. But remember that this molecule, as I'm looking at it, it looked the same no matter how I put it. I can't cut that carbon away from those hydrogens and get a positive side and a negative side to this molecule. I just can't do it. Okay? So because of that, this is a nonpolar molecule, and the only forces that attract it to another molecule just like it are LDFs. Okay? Everybody okay so far? This is also ones that we would use to describe diatomic molecules and their attraction to each other. Come on. Just want, oh. Okay? They have LDFs. All right, we're going to go down to the second strongest, which is known as dipole-dipole. Second strongest IMF. The first one, the LDF, is the weakest. Dipole-dipole is the second strongest. Okay, pole. What does pole mean? If I have a pole, what does it mean? North pole, south pole? Okay, usually it's a side, a charge, or a pole, a positive, negative. Okay, so we have a molecule that I can get into a positive, negative. It doesn't have to be a full positive and negative. In fact, it's not a full positive or negative, so we use the little delta signs. Okay, so geometrically, I can get a positive and negative. Let's take our CH4, which is right here. and make it CH3Cl. Okay, so we're going to take our carbon, put it in the center, and we're going to take a hydrogen and put it up here, and a hydrogen and put it over here. I'm making these hydrogens a little big so I can see them. And a hydrogen and put it here. And then I'm going to take and I'm going to put a chlorine over here. Okay? Well, we already know from up above that our hydrogens are going to be, whoops, I missed my color, are going to be slightly positive. What do we know about chlorine? Does it want to give away electrons or take in electrons? Take in. It wants one more, right, to be like a noble gas. So it's actually going to be a negative. And so we actually have a negative center part. Carbon is sort of neutral kind of thing. But we can actually take and say, I've got a positive side and a negative side for the most part, because this one sort of can fly over there a little bit. Sides to molecule. So I can get a slightly positive side and a slightly negative side to the molecule. If we go like this overall, you can sort of see I have a negative over here. I have positives on this side. Can you see that? This is a dipole-dipole. Okay, this is a dipole-dipole. Another way we could draw a dipole-dipole would be like H2S. So if we were to do S has 6 electrons around it, right? And we would come in with a hydrogen here and a hydrogen here. And from what we know already, hydrogens want to be +1, right? So we're going to have a slight positive because these aren't strong enough to pull away totally the electron. And the sulfur wants 2 negatives, right? It wants 2 negatives, so it's this side over here is going to be slightly negative. So as I'm looking at the molecule, I can basically, whoops, I shouldn't cut it through the molecule. I basically can, all right, I'm going to have to redraw sulfur, sorry. I can actually split the molecule here and have a negative and a positive side. So that is a dipole. Okay? So this is the second strongest, or second weakest, whatever you want to call it. Okay? There's one more. This one more is called hydrogen bonding. Now, there are actually a lot of scientists that are saying, you know, this one is so strong, it should actually be considered a bond. Okay? And so that's why it's got the ending of a bond. But there's some that say, you know what, it's just not quite there. It's not really a bond. It's just more of a really strong attraction. This happens between nitrogen and a hydrogen, oxygen and a hydrogen, or fluorine and a hydrogen. So I call it NOF with a hydrogen. And if you look on the periodic table where nitrogen, oxygen, and fluorine are, they're on the second row and they're right next to fluorine. So they want electrons really badly. So let's take one NOF thing that we could look at very simply, which is water. So as we look at water, we would draw this, and then we bring in a hydrogen, put it here, and a hydrogen, and put it here. This looks a lot like what the H2S did up above. Okay? As I'm looking at this, I'm also going to have, by the way, and I forgot to tell you this before, if I have this bond, I also have dipole-dipole for the most part, and I also have LDF. The only time I don't have one is if it's symmetrical. Okay, so here I have hydrogen bonding because it's an oxygen to a hydrogen. I have dipole because this side is slightly positive, this side is slightly negative, and I have LDFs just because it's a molecule, it's a compound. Okay, so this one has all. It has LDF, dipole-dipole, and hydrogen. Now, when this becomes important is when I get a whole bunch of waters together. So I'm going to do a shortcut here and just sort of show water like this. Okay? What happens is, remember, the oxygen side is slightly negative. Hydrogen side is slightly positive. And so it attracts another oxygen right here. and this one attracts another oxygen right here. And they're not really bound, but they are so attracted, it's almost like a bond. So you notice when you freeze water, it expands. It expands because it has to allow for this arrangement. When it's a liquid, they sort of bypass each other, and if we get a negative next to a negative, they push away, and if we get a negative next to a positive, they attract each other, and they sort of flow over each other. But when we get a solid, they have to arrange so that you got a positive side and a negative side. Okay? This is hydrogen bonding. This is why water skeeters can land on water. This is why the meniscus happens. Okay? This is because of hydrogen bonding. So let's look at another one that's hydrogen bound. Nitrogen with hydrogen. So we bring a hydrogen in here, we bring a hydrogen in here, we bring a hydrogen in here. What do we know about this unshared pair of electrons at the top? What have we learned the last little bit about them? This unshared pair of electrons, I sometimes call a ghost. Doesn't it actually bring nitrogen up out of the plane and force hydrogens down a little bit below them? Okay, so I get hydrogen bonding because it's nitrogen to a hydrogen, but I also have dipole-dipole because this nitrogen side will be negative and this hydrogen side will be positive, and I have LDFs. Okay? Any molecule will have LDFs. So that's like the lowest, everybody has it kind of thing. Okay? So I can attract another nitrogen underneath just like this, or another ammonia, and it will come and it'll start attracting like this. Okay? All right. So this is how I sort of think about it. LDFs, you're all in the classroom. Okay? So we're all close together, so we're going to have some LDFs. Dipole-dipole. You get to be friends. Okay? So you get to be friends. And you come a little bit closer. Then you get to hydrogen bonding. Oh, this is when we pair off and we have boy and girls. Girlfriend, boyfriend kind of thing going on. Okay? So we get a little bit more serious, a little bit more bound to each other. Okay? This is how it works in chemistry. All right? But I'm just putting it into your world.